Node.js is an event-driven platform for writing scalable network applications. But what does that mean, really? We talked a little bit about it back in episode 1, but that was some pretty high-level detail. Shortly behind knowing the JavaScript language itself, understanding the event queue is one of the foundations of success to using the Node.js platform. In this episode, we're going to really dive into what event-driven means. I'm going to touch a simple file here. We'll call it program.js. I can run this file using Node. Just like we'd expect, nothing happens, but we can see that the program terminates. We can make it more interesting, and then run that. How is this working? What does the process Node do? Now I've blathered on about it, and when you read about it, you read that Node.js is an event-driven platform. It's beyond our scope to talk the finer technical details about what events in computer programming are, but here's a way we can think of it. When I run the program Node, I start a process that creates a few things. First, it creates what we call an event queue. Queues are a basic computer science concept, and if you're unfamiliar with the term, I provide a link to Wikipedia explaining what they are. Node also creates what I'm going to call the ether. I use such a vague term because our application isn't really concerned about the particulars of what goes on there. Here's what makes Node event-driven. Node is simply a program that runs the JavaScript code you write or pull in via packages in response to events placed in its event queue. That's it. That's all it does. I call that JavaScript you write or pull in application code. Node the program terminates when it has run out of events to run and there is no chance of it receiving additional events. But here's the catch. Node only does one thing at a time. That is, if it's running any particular chunk of application code, it is not running any other chunk of application code. Much like Highlander, there can only be one. We call the processing of one of these chunks a tick. Thus, a Node program is just a sequential processing of ticks. Now I don't know if the internals of Node.js call it this, but we can think of our initial invocation as an event whose response is the contents of the file we ran. So when we run it, we toss an event into Node's queue to let it know to run our file, and it does. Then it exits, all is well. Well, what if we want to do something useful? Well, that's a different matter, and it's here that we'll see what we mean when we talk about asynchronous code versus synchronous code. Suppose that we want to write a program that reads the contents of a file and puts them on the screen. Yes, you could just use cat on a Nix system, but dang it, we have wheels to reinvent. We're going to illustrate this difference via two versions of the same function. So let's create our file that we're going to read, just echo I'm in a file. And let's create our file that will read and display it. We'll call it cat.js. We're just going to use one of Node's built-in libraries, namely fs, which stands for file system. That seems like a good place to get functions that deal with, the file system. Now let's add in some code that will read the file and let us know when we're done. var data equals fs read file sync text.txt, and then we'll log the data and log our all done message. Let's run it. Node cat.js. Voila. Let's break down what's going on here. First, Node spins up and creates an event queue and ether. Into the event queue, it inserts the contents of our file. Since we're at the front of the queue, the first tick will be running the contents of cat.js. We create a space in memory where we store the fs module. Then we call into read file sync, which returns to us the contents of the file. We display those contents, and then we display our all done message. That probably looks a lot like what you're used to in platforms that don't call themselves event-driven. But there's a problem. Remember how we said, Node only does one thing at a time. That is, if it's running any particular chunk of application code, it is not running any other chunk of application code. Much like Highlander, there can only be one. Read file sync is a synchronous call, which means our program sits there and waits for the contents of the file. Our tick doesn't run to completion until after we have read the file from disk. In this particular example, it's not really a problem, but imagine if this were a really large file, or we were writing a web server with web scale popularity like Node/, the project we've slowly been developing in Learn All the Nodes. The severity of this is that while we are sitting and waiting for the file contents to come back, our program becomes entirely unresponsive. One, and only one tick can be run at a time, and we haven't released control. That is what synchronous execution means. In episode 1, we talked about how other platforms overcome this problem by just spinning up additional threads or something like that. That can get memory intensive, and so I think it's suboptimal. To handle additional things at the same time, we have to spin up additional copies of such programs. This is the problem that an event-driven architecture solves. So let's look at this program again, but from an asynchronous viewpoint. Let's start a new file called catasync.js. And we'll put in this stuff that you're seeing right here. Now this file has 3 steps. The first 2 are simply definitions, fs and do something with the text. The third thing we do is call fs's readFile, not readFileSync function, passing it 2 arguments, namely the path to our file and do something with the text. Remember that in JavaScript, functions are first-class citizens, which means they can be passed around just like anything else. And then our tick is over. Node then goes to the event queue and finds nothing else there, so our program should terminate, right? Well, not quite. Remember, Node the program terminates when it has run out of events to run, and there is no chance of it receiving additional events. Our call to read file did something interesting. It is an example of what we call an asynchronous function. What this invocation means in English is, fs, I want you to read the file found at this path. When you've gone out to do that, here's a function, do something with the text, that I want you to call with your results. Fs says, okay, and tosses this all out into the ether. It's from the ether that additional events can come, and Node the program is aware that there's something in the ether that could cause an additional event, so it doesn't terminate. It's so important to note that when fs readFile returns in the sense of a function call returning, we haven't actually read the file. The call to read file is more like scheduling a file to be read than it is the actual reading of a file. We've queued up a file read in the ether and given it a point to return to when it's done. Now the ether can run as many things at the same time as your hardware's memory can support. When we say Node.js is single-threaded, we only mean that the application code is single-threaded. Only one event tick can go at a time. Lots of stuff can go on at the same time in the ether. At some point, the read attempt will go through, and it's important that we call it an attempt, because it may have failed, and that's why our callback signature is so important. Looking at the node docs for read file, we see that the callback is passed 2 arguments, air, data, where data is the contents of the file. Every asynchronous function in Node, whether you write it or not, is going to have some contract about what a supplied callback must look like if you want meaningful results. In this case, our function should have 2 parameters. The first, and this is a foundational Node concept, is an error object. In a lot of languages, when you do something like reading from a disk, and you want to be careful and not crash, you'll surround the call to the file system with a try-catch block, or whatever your language calls that. This doesn't work with read file because remember, the call to read file doesn't actually read a file. It schedules a file to be read out in the ether and gives us a reentry point when the attempt is made. If you wrap that call in a try-catch, you're likely never to see an error because scheduling the read is an extremely safe operation. At the risk of beating a dead horse, let me say that again. Read file doesn't actually talk to the disk. If you wrap it in a try-catch, you're wrapping the scheduling of the read in a try-catch. Now, one way we could have written this is to just pass the function directly in line like so. But I think this is more confusing because it looks like the call to fs.readFile reads the file. By separating the function definition, I think it's much clearer how it actually works. But that's a style call you'll get to make in your own apps. But disk reads are still error prone. Not even Node.js can fix that. And they're likely to fail sometimes. That is the purpose of the error parameter in the callback. If something goes wrong, and that could be disk failure, getting the path to a file that isn't there, whatever, the ether calls back into our callback, passing an object that will explain what the problem was. It will be an object of type error, and you can read about it at the Mozilla doc I linked to in the show notes. It'll contain a message and other information like a stack trace. It's good stuff. So instead of invoking exception handling machinery, errors are taken in stride and just returned as run-of-the-mill objects. This is why every asynchronous callback I can think of takes an error argument, and why you should always check the value of that error object in your callback, like how I edit do something with the text here. I use the return as a way to break out of the function, and that's just a style preference that I have. Now, if there wasn't an error, then text buffer is going to be an object holding the contents of our file. We then just output those to the console, output our all done message, and then our callback terminates. At this point, Node the program knows that our tick in the event queue is done. It then looks for another event and doesn't find one. Since readFile can only generate one event and we've already fired it, the ether also can't generate an event for us. This is the point at which Node the program terminates, and we return to our command prompt. You might be wondering how this works with web servers. If you remember episode 2, and why would you? I hardly remember that episode and I made it. Server.listen can endlessly generate events, and that's why Node the program keeps on running. You can see the doc on what kind of an object server is here, and you'll see it's an event emitter. It'll just sit there in the ether, tied into your computer's networking capabilities. When it gets an HTTP request, it bundles that request up into an HTTP incoming message object and passes that to our handler along with an HTTP.server response object that our handler writes a response to. We saw in episodes 3 and 4 how the base node HTTP server can get quickly out of hand when we want to add additional endpoints to our application. We introduced Express to solve that. Express just gives us a nicer interface for dealing with HTTP incoming message and HTTP server response objects. A Node web app, even one that uses Express, is simply a script that ends up pushing an HTTP server into the ether that's configured with a callback to respond to HTTP request events. No magic. Now we should call out one last thing about ticks. Our callback function itself calls other functions. Console.log is a synchronous function, for example. We could also call into all sorts of other functions that we write ourselves, but our tick ends when the first function called into from the ether ends. We could queue up all sorts of other things in our callback, additional file reads, network requests, to send our file content someplace else, etc. But our current tick ends when do something with the text runs to completion, since it was the first thing called into from the ether. And that's what the event queue is all about. I hope this dive into how it works has been useful. There's more we need to talk about though. While we did talk about ticks, there are some other interesting functions we can use to control when certain things happen. What if you have some operation you want to do, but you don't want it to occur in the current tick? We'll get into that in the next episode. Until then, happy coding.